Here at a conglomerate, a pebble conglomerate. We've got some moss, little bits of moss on it. Um, so this grain might be a centimeter across. There's some kind of layer of probably um, limestone here. And this is a 3D model actually that we can move around in. If we look at the top of this, whoa, it looks like it's entered kind of into hyperspace, right? Like what is going on here? These grains we're looking at, when we look at the top, we see that they're, look at this one here. They're super stretched out, right? They're shaped like it's like blades, sword blades. Okay, so this is the kind of thing that motivates structural geologists to be interested in calculating strain. We want to be able to look at something like this and quantify it. Um, so we can figure out, like, well, how much has this area of rocks, been stretched or smushed. So the next bit of the lecture talks about three-dimensional strain. We can't just look at this one side, this one face. We really need to be thinking in the third dimension. Even though this looks kind of normal, it almost looks like it could have just been deposited this way and not be strained at all. When you get over here, you see, indeed, there's been a lot of strain happening. Here's another example. We see a little backpack for scale, a rock hammer. Look at how long these cobbles are. In this case, they're much bigger. And then we look in this direction, and we can see, yeah, look, these rocks, they're relatively round. This one not, maybe a little bit, maybe have an aspect ratio of 2 or 3 to 1. Much different in that dimension than when we look in this dimension, look down on it, quite a bit longer. So this is a 3D strain situation. So I mentioned circles earlier. We said that homogeneous in homogeneous strain, circles become ellipses. So homogeneous in 3 dimensions, we can say that homogeneous strain can be described by an ellipsoid. So an ellipsoid are very specific mathematical entities. An ellipse is like an oval shape. An ellipsoid is a three-dimensional kind of bean shape. So in 3 dimensions, if we start out with a sphere, see if I can draw a sphere. Try this again. Trying to draw a sphere here. Okay, so imagine that's a sphere. That is going to turn into, let's see if we can draw some 3-dimensional axes here. Sort of this ellipsoid. So ellipsoids have 3 axes. So if you were to draw lines through the center of an ellipsoid, there's a line you could draw that would be the longest line that would go through the ellipsoid. That line we call S1. So S1 is the maximum stretch. So that S, that's the same stretch that we defined earlier. It was the final length divided by the initial length. So the longest thing here, we define it as S1, the longest stretch. The smallest stretch here would be S3, and the intermediate one, S2. This is intermediate stretch and minimum. And we call these S1, S2, and S3 the principal axes of strain. These are supposed to be quotation marks. Okay, so any kind of homogeneous strain, we just did this in 3 dimensions. We could also do it in 2 dimensions. So, for example, just in the plane of the screen, start out with, if we were to draw a circle on this box, and then we were to smash the box, the circle becomes an ellipse, and we could measure the longest and the shortest lines that go through the center. And call this S1 because it's the longest. It's this, and this here is the shortest, S3. So what we've drawn here is a special case of what we call plane strain. So just backing up for a second. So there's something called plane strain. And this occurs when S2 equals S1 times S3, which is equal to 1. So in other words, it's representable on a 2-dimensional surface, like the screen. Okay. So S2, we're assuming here that there is a 3rd dimension, but that this length hasn't changed. So it's in that dimension, the length final is equal to length initial. And so when you look at the formula for stretch, the same numbers divided by each other are 1. So if this is a case of plane strain, S2 is 1. Let's say that S1 we've doubled the length of this long axis. That would be S1 equals 2. This formula tells us then that S3 must be 0.5. Okay, so there are sort of special cases of plane strain. Pure shear is one of them. Pure shear has elongation in one direction and shortening perpendicular. So that's the symbol I'm going to use for perpendicular. So that's what we drew up there, right? We elongated in this direction at 90 degrees, so that we shortened. The other special case of plane strain is called simple shear. And this is the sort of deck of cards type. So we can imagine some, get a different color here. Some line drawn on here. And we'll faintly sketch some other lines as well. Okay, so when we shear this, and so remember, so we're doing this is a type of plane strain. So we're not, nothing's, there's no, in the third dimensions, nothing's happening. We get an ellipse. That circle that we drew became an ellipse. That ellipse has axes. The long, like just as before, the longest line we can draw through it, we call S1. The shortest line we can draw through it, we call S3. And because of the magic of ellipses, these will always be at 90-degree angles to each other. And that line we drew will have, you can just kind of intuitively see that it will have rotated. So a third type of special case of plane strain is simply a combination of pure shear and simple shear, which we call general shear. So in this case, we, so both, we do some, We change the height of the box and also shear it to the side. So in all three cases, remember, these are plane strain. In other words, in that third dimension, S2 equals 1. So there's nothing coming in and out of the page. It's not getting longer or shorter in that third dimension. And what that means is that the surface area, if we were to shade the area of this circle or the area of this box, they would remain the same. So this circle should have the same surface area as this ellipse that we've drawn. In general shear, in simple shear, and in pure shear, because those are all types of plane strain where we're not gaining or losing any material out of the plane that we're looking at.